Hello friends, you are watching ERUDIRE PLUS, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'll show CFD analysis through a condenser heat exchanger using ANSYS Fluent fault tolerant meshing. You can see this is the model. From this opening, we'll provide freon gas at a higher temperature and pressure, and we're having a lot of fins, and while passing through these fins, a huge amount of heat will be lost, and finally it will change its phase from gaseous stage to liquid stage, and finally it will come down to room temperature, right? What we're planning to do is, from this opening, we'll provide freon gas at higher temperature and pressure, and while it will pass through these different pipes, you can see there's different types of spiral pipes are there, and while freon will be passing through these pipes, it will suffer change of phase, and finally at the exit it will come down to room temperature with liquid phase. Let us understand the model in a better way. See, backside we are providing some kind of fan space. From backside we can provide free flow of air, and that can be done using fan. Here in this case, instead of fan, we'll be providing free flow of air at a specific velocity. It will serve the same purpose of a fan, right? It is actually external analysis. With some attachment, we have made this one an internal analysis. Let us see the other parts, what it is having. Let us show all the parts. To make this one as an internal analysis, what we have done is we have made some kind of casing, and let us see this one better way. We have provided different domains for freon and air. From this one, we'll provide freon at high temperature and pressure, and from back side you can see here we'll provide air at a specific velocity. And as it is an internal analysis, so what we'll do is this one will be having some kind of cover, right? So front side will have some kind of cover, and this is the exit of freon. Here in this case, freon will suffer change of phase from gaseous stage to liquid stage, and finally at the exit it will come down to room temperature. Okay, to start simulation, we need to save this model in FM database with the extension of FMD. The model has already been saved, so let us close it. We need to start Fluent launcher. Let us start it from here. Initially we need to open fault tolerant meshing from here. Then we need to import that component with custom settings on from here. Let us load it. We need to drag this component into meshing model. We need to create meshing objects. We can see this is the object. Let us have a complete view of this one. We have provided some kind of casing to have specific amount of air inside this domain. We are considering this one as an internal analysis. That could be considered as an external analysis also. So with some specific setup, we are considering this one as an internal analysis. So here in this case, at this location, we need to define what type of analysis it is. Basically, it is an external analysis, but we are converting this one as an internal analysis with some specific setup. Within this specific casing, we need to provide some kind of air. By the same time, from this side, we need to provide freon at a high temperature and pressure. Okay, so from here we're considering this one as an internal analysis, and with other default settings, let us describe the geometry and flow. We know that in CFD analysis we need to have a closed volume. Here in this case we're having 4 different openings, 2 entries and 2 exits. So those openings should be closed using caps. Let us provide those caps one by one. Let us select freon inlet, and zone type will be velocity inlet, and we can rename this one as cap 1. From cap 1, we'll provide freon at a high temperature and pressure. Okay, so cap is created at entry of freon. You can see this is the cap at the entry of freon. Next to that, we need to provide cap at the other different openings. Next to that, we need to provide cap at the inlet of air, that is at the back side where inlet. Again, zone type will be velocity inlet, and we are keeping the name of this one as cap 2. Let us create cap. Let us see whether cap is created at backside or not. Yes, cap at the entry of air is also done. Next to that, we need to provide caps at the exit locations. We can select Freon outlet, and in this case zone type will be pressure outlet as it is the exit. So pressure outlet, and we are keeping the name of this one as cap 3. Let us create cap at the exit of Freon. We can see this one, whether it is done or not. Yes, cap is created at the exit of Freon also. Next to that, finally we need to create cap at the exit of air. So selecting air outlet, and again zone type will be pressure outlet, and we are keeping the name of this one as cap 4. Let us create cap at the exit of air. So you can see 4 caps are created, and it is a closed volume. It is ready for CFD analysis, right? Next to that, we need to identify regions. That means we need to identify different fluid domains. In this case, we are having 2 different fluid domains. One is Freon and other is air, right? And for identifying different fluid domains, we are having different options like centroid of objects or numerical inputs and offset methods. In this case, we'll use offset method, right? First of all, we need to provide Freon zone or Freon domain that is coming from cap 1. You can see one diamond shaped object is there. So that diamond shaped object will indicate the location of Freon domain. That's why the diamond has to move inside, and that movement can be done using offset of x value in the negative direction, right? So you can select here offset methods, and it will move in the x direction. Let us provide x equal to minus 50. Let us see whether the diamond is moving inside or not. Yes, the diamond has moved inside. Now we can check it very clearly using clipping planes. Yes, the diamond is showing the domain of Freon, which will be passing through these copper tubes, and we can rename this one as Freon domain. Let us identify this Freon domain. It is done. Next to that, we need to identify air domain, and that should pass from the backside. So that is cap 2. You can select cap 2. To indicate air domain, the diamond has to move inside, and that will be done by the offset of z value in the positive direction. So from offset method, we need to push that diamond into the z direction, right? We can see here it will move in the z direction. Let us put z equal to 17, which is indicating the domain of air. You can see from inside this is the domain of air. This from backside will provide air at a specific rate, right? These air particles will pass through these fins, and it will cool Freon, right? So with this one, we can identify this is air domain. We can rename this one as air domain. Let us identify these 2 domains have been defined, Freon domain and also air domain. Next to that, we need to identify some kind of void domain, which is required to restrict the flow of fluid from inside to outside. Next to that, we are creating one void domain for indicating void domain. Let us select that object, and the demon shape has to move outside this domain. For that, what can we do is we can move that offset value in the upward direction, that is in the positive direction of y. Let's take y equal to 250. The demon shape is outside this domain, which is indicating void domain. Let us rename this one as void region and identify this one. So we have defined three defined domains, that is freon domain, air domain, and also void domain. Excluding that one solid region will be created. As it is a heat transfer analysis, this solid region also will be required. Okay. Next to that, we need to define leakage threshold, and in this case we are not having any kind of leakage, so we can move with no leakage condition and update. You can see here different domains are there. As I told earlier, 4 different domains are created. Object is the whole setup. Here in this case it is showing as void, but we need to convert this one as solid, as it is a heat transfer analysis, so we need to consider the solid domain also. So in our case, we need to consider these two fluid domains and also solid domain, and each of the different domains can be meshed separately. We're considering these two fluid domains to be meshed with polyhexagonal meshing, and solid domain should be meshed with tetragonal mesh. And this air domain and freon domain we're considering as polyhexagonal meshing. With this meshing setup, let us update these regions, and with default mesh control options, let us update. Now we need to generate the surface mesh, and in this case the target skewness is 0.8. Let us generate surface mesh. You can see here surface mesh is generated, and overall summary says skewed cells more than 0.8 is 35, and average skewness is 0.08, maximum skewness is 0.99, and base count is 0.38 million. You can see left hand side different boundaries have been updated, and as expected we got 2 inlets and 2 pressure outlets. Cap 1 is indicating inlet of freon, and cap 2 is indicating inlet of air, and similarly cap 3 and cap 4 are indicating outlet of freon and air respectively. Excluding that, we are having a lot of walls. All these walls are very important, and through these walls it will be transferred through convection. Let us update these all boundaries, and in this case we don't want any kind of boundary layers, as the diameter of copper tube is very less. Let us avoid this one, and with no boundaries let us update this one. And finally we need to generate the volume mesh, and in this case we will consider quality improvement limit as 0.04. Let us generate volume mesh. We can see here volume mesh is generated. You can see it from clipping trends. can see it from different planes. What the summary is saying that quality less than 0.1 is 521, quality less than 0.04 is 110, and minimum quality is 0.15. You can see the quality of mesh from here also. Mesh quality is showing that minimum orthogonal quality is 1.5 into 10 to the minus 2, and maximum aspect ratio is 1.4 into 10 to the 3. With this mesh quality, let us move on to solution mode. With this solution mode, first of all, we need to select units. And we'll consider length as millimeter, and temperature will be degree centigrade. Close it. It is a steady state analysis, and in this case gravity will be involved, and the direction of gravity will be y as indicated by the green arrow here. So along y direction it will be minus 9.81 meter per second square. Next to that, we need to select models, and as it is a heat transfer analysis, so energy equation should be on, and it will be K epsilon turbulent model, realizable and scalable wall functions. Next to that, we need to select materials. In this case, we are having two different fluids, air and freon. Air is already there, so we need to select freon from Fluent database. We're considering freon 12, copy, and solid we will consider copper and aluminum. Copper will be used for tubes, and fins will be made up of aluminum, right? So let us select solid material as copper, copy, close. We have selected air and freon as fluid and aluminum and copper as solid. Next to that, we need to select cell zone conditions. In this case, we are having two different domains, fluid domain and solid domain. And fluid is also having two different domains, air and freon, and that to be defined from here. Air domain should contain air as the fluid. Apply, close. And freon domain should contain freon only. Apply and close. Next to that, we need to define solid. Mainly we will consider copper tubes. So material here will be copper. Apply and close. And the fins will be made up of aluminum that will be provided during applications of boundary conditions. Next to that, we need to apply boundary conditions. In this case, we are having two different entries or inlets. Cap 1 is indicating freon zone and cap 2 is for air zone, right? So from cap 1 we'll provide freon at a specific temperature and pressure. Let us provide velocity of freon as 0.1 meter per second, and we'll provide at a high pressure of 0.2 megapascal, that is 2 into 10 to the 5 pascal. And consider this one as 2E5. That is 0.2 megapascal, and we'll consider temperature of freon as 75 degrees centigrade. So it will be in gaseous stage. While passing through these cover tubes, it will suffer a huge amount of heat loss, and finally it will be converted to liquid stage at room temperature. Let us apply and close. Next to that, we need to apply air. From back side, we will provide air at a specific velocity. This will serve the purpose of a fan. We are considering velocity of air to be 0.01 meter per second, and temperature of air will consider as 20 degrees centigrade. That is normal temperature. Apply and close. And we see the outlets. We are having two outlets. It is freon outlet and also air outlet. Both of them will be having 0 gauge pressure. Let us consider freon outlet. Its pressure will be 0 gauge pressure. Apply and close. Similarly for air outlet also, it will be having same boundary condition. That means it will be having 0 gauge pressure at the exit. Apply and close. Next to that, very important is walls. Actually, walls are made up of aluminum, and by the same time we can see different copper tubes are also there. So copper tubes and fins will be provided different boundary conditions. We can see here air inlet, air outlet, casing, all are made up of aluminum, and condenser is basically made up of copper, right? So we'll select first condenser, which is made up of copper. These are mainly the copper tubes. So from these tubes, it will be transferred by convection, and it will be made up of copper. We're considering convective heat transfer coefficient as 20 watt per meter square degree Kelvin at a temperature of 30 degrees centigrade. And wall thickness we're considering as 0.01 millimeter. Let us apply and close. Same boundary condition to be applied for the remaining copper tubes. Let us copy, and that to be pasted to the remaining copper tubes. Let us select all these things one by one, and also freon inlet and freon outlet. These two are also made up of copper. All the copper tubes are selected, and let us copy it. So similar boundary conditions are being applied for the remaining copper tubes. Let us close. Next to that, we need to consider fins, and all the fins are made up of aluminum. Let us select the first one. Fins are made up of aluminum, and it will be transferred through convection. And here in this case, we are considering convective heat transfer coefficient as 15 watt per meter square degree Kelvin at a temperature of 30 degrees centigrade. And we are considering wall thickness as 0.01 millimeter. Let us apply and close. Now same boundary condition to be copied and pasted to the remaining fins. Not only the fins, together that this casing also is made up of aluminum. So we have to select the air inlet, air outlet, casing, and all the fins are made up of aluminum. Let us copy, and the similar boundary condition is applied to the remaining fins and casings. Let us close it. All the boundary conditions have been applied. Next to that, we need to select solution methods. It is coupled method, and special discretization we are selecting green gauss node based method. Pressure will be second order, momentum also second order upwind, turbulent kinetic energy also second order upwind, turbulent dissipation rate second order upwind. Next to that, we need to start initialization. Let us consider standard initialization, and it will be initiated from all zones. Let us initialize. Initialization is done. Next to that, we need to run calculations, and let us consider 100 numbers of iterations. Let us calculate. Iterations have already started. Let the iterations move on. Whenever it is finished, we'll see the results and go for detailed analysis. Okay, calculation is complete. Next to that, we need to see our results, and results will be viewed from reports, surface integrals, and report type, facet average, and we want to see temperature distribution at different locations. Mainly we want to see temperature distribution at the exits, so it will be cap 3 and cap 4. Excluding that, we want to see temperature distribution at fins. Let us include cap 1 and cap 2 also, that means the inlet temperatures. Let us compute. We can see the temperature at cap 1, that is the entry of freon, it was 75 degrees centigrade, and cap 2, temperature at the entry of air, it is 20 degrees centigrade. These values are actually provided from boundary conditions, so these are not the results. Our results are actually at cap 3 and cap 4. Cap 3 is the temperature at the exit of freon, which is 22.85 degrees centigrade. That means we got a huge reduction in temperature of freon. Initially, temperature of freon was 75 degrees centigrade. It was in gaseous stage. Finally, it has been converted to liquid phase at a temperature of 22.85 degrees centigrade. And finally, the temperature at the exit of air, it is 21.27 degrees centigrade. And temperature at the fins, it is a little bit high, it is 29.65 degrees centigrade, and net temperature is 22.24 degrees centigrade, right? Next to that, we want to see results from different contours of temperature and pressure. So first of all, we want to see contours of temperature. And it will be from freon domains. You will see from condenser freon domain. Let us display. We want to change the temperature range, because we know the temperature range is actually from 20 to 75 degrees centigrade. So we can change the temperature range from 20 to 75 degrees centigrade to have a better representation of temperature distribution. You can select the range from 20 to 75 degrees centigrade. Let us display. This is better representation. That means you can see at the inlet temperature is a little bit of high, which is in the range of 75 degrees centigrade, and throughout the pipes temperature is almost constant. It is in the range of 20 to 22 degrees centigrade, right? Next to that, we're going to see pressure distribution through this same domain. Let us display. This is showing pressure distribution. You can see clearly that when freon has been converted to liquid phase, pressure is very high, right? But temperature is very less. So temperature remaining constant at the end only. Temperature is in the range of 20 to 25 degrees centigrade, but pressure is very high at the exit. When freon is converted to liquid phase, pressure is very high. Right? Next to that, we want to see dynamics of flow particles, and that can be viewed from path lines, new path lines, and particle variables. It will be temperature, and we want to see temperature distribution of flow particles through freon domain. Let us display. This is the distribution of freon flow particles through inlet to exit of the pipes. It will be better to see these things in the form of animation. So let us have a pulse of it. You can see how the freon particles are moving from inlet to exit. Let us stop it. This one is representing flow particles of freon in terms of pressure distribution. It will be better to see these things in the form of an animation. Let us have a pulse of it. These are dynamics of flow particles of freon in terms of pressure. You can see here at the inlet of freon, pressure is high, but at the exit, pressure is much higher. Here in this case, freon has been converted from gaseous phase to liquid phase, and finally its temperature is less, in the range of 20 to 25 degrees centigrade. Right? Let us stop it and close. So with this one, we'll conclude our today's analysis. This is a very simple analysis of condenser heat exchanger. In this case, we have provided freon gas at the inlet at a higher temperature of 75 degrees centigrade, and finally at the exit, it has changed its phase from gaseous state to liquid phase, and it has come down to a temperature in the range of 20 to 25 degrees centigrade. Right? And this temperature reduction was possible because of fins, and we have provided a huge amount of airflow. Right? Thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.